Hi, my name is Alice. I'm from Boston Latin School, and for the past few years, I've been doing intensive research in the field of quantum computing, specifically quantum machine learning and quantum optimization methods for implications in the medical and the healthcare industry. Today, I'll be presenting a project that I've been working on for the past couple of months that harnesses quantum machine learning on breast cancer detection that's tested on a quantum computer from IBM. Now, with our current state, there's over 3 million individuals who are diagnosed with breast cancer in the US. The misclassification of breast cancer cells happens around 20% of the time, and late or misclassified diagnosis of breast cancer can decrease an individual's chance of survival from 90 to just 15%. A lot of research today is geared towards using machine learning to more accurately classify cancer cells, but even those techniques have limitations to it in terms of computational complexity. Now, before diving into the project itself, I want to discuss our current state with machine learning. Support vector machines, or SVMs, are a supervised learning algorithm where given data will output an optimal hyperplane that's able to categorize new examples. And, this is pretty easy for a 2D data set. You just add a line right through it to divide the samples. But what if you add another dimension with a 3D data set? Here, it's not as straightforward to find that hyperplane, but by using a kernel trick, we're able to map this data set to a higher dimension in order to find it. Now, this trick is effective, but what if the dimensions become higher and more complex from 3D to, let's say, 100D? This takes a lot of computational power, which can take up to weeks to train. And our current classical ways of computation are just simply not efficient enough. But this can potentially be solved using quantum machine learning, where information can be run on quantum hardware to allow for a quantum speedup and optimization during processing. Quantum machine learning is a hybrid of quantum computing and AI. This specific area exploits the benefits of the quantum mechanical properties or quantum advantages that are enabled for faster and also more optimized computation, as well as the established algorithmic models and computational infrastructure from our current machine learning. And this is based on the idea of amplitude encoding, where amplitudes can be used to find optimization routes, and that leads to an exponential reduction in the number of steps during computation. But how is this better than our current approach? Quantum computing relies on quantum mechanical properties such as entanglement and superposition. The fact that qubits or quantum bits can be in superpositions of zeros and ones, or let's say a 100 qubit processor can run 2 to the 100 calculations simultaneously, is much more efficient than today's one by one at a time approach. And that allows for speed up and also better optimization. So with this, my objective and my main research question is how quantum computing methods can speed up the process during clustering, with a hypothesis that the quantum SVM with a 2-qubit simulation would yield the highest classification results. For the experiment itself, I tested the accuracies when dividing breast cancer cells as benign or malignant using 4 different approaches. A classical SVM ran on a CPU that functions as the control of the experiment, the quantum SVM algorithm with a 2-qubit, a 4-qubit, and also an 8-qubit simulation. And the percentage of cells correctly classified into their groups will be outputted, and that acts as the dependent variable. And all the implementations of this experiment was done entirely on Python. The quantum processing unit I used was by leveraging the API of IBM's cloud quantum processor and integrating that with my local machine. And in terms of the data I used, and the data extraction processing, I utilized a breast cancer cell dataset from the UCI ML repository, and that contained data features on the cells such as texture, perimeter, and area. In terms of the algorithms used, the SVM algorithm relies on finding the decision boundary with the widest distance of margin from each support vector in order to find and draw that optimal hyperplane that will separate the different class guys and categorize the different groups. So a function representing the maximized constraints for the distance between the support vectors can be outputted. A kernel trick is then applied to find the optimal hyperplane that's able to divide the samples into different classification groups. And the quantum SVM algorithm is able to take the same framework as the classical SVM algorithm and perform it on a quantum circuit by mapping the data to individual quantum states, while applying binary measurements and also computing the empirical risk. In the actual implementation, a pre-processing is needed, and also using principal component analysis, or PCA, to fit that data dimensions based on the number of qubits. And the data set was divided into 70% training and 30% testing. The data was then standardized and scaled. In the implementation of the quantum algorithm, the dimensionality and the feature maps are set, and the parameters for the algorithm to train on are also set, including the circuit depth, number of shots, and also initializing the pseudo-number generator. Now, during the pre-processing, in terms of results, the relationships between the different features are outputted, including the radius, texture, smoothness of the cells. With the PCA, the dataset was reduced from 5 parameters to 2 principal components, which is able to increase interpretability while also minimizing for information loss. With a classical SVM algorithm, a correlation matrix and its performance measures are displayed for an overall classification accuracy of 85%. Now, with a quantum SVM algorithm for each implementation of 2, 4, and 8 qubits, a kernel matrix is built from the training sample of the dataset with the different classification accuracies outputted. So as an overview for results, the quantum SVM algorithm with a 2-qubit simulation yielded the highest classification accuracy of 90%, and the quantum SVM algorithm with the 8-qubit simulation had the lowest result of 65% for the classification accuracy. And as a result, this result supports the original hypothesis, with the 2-qubit simulation having the highest classification accuracy. The 8-qubit simulation having the lowest accuracy is likely due to current limitations in our quantum processors, with a greater likelihood for the number of qubits going into decoherence. Now, quantum computing is just like the internet from the 70s in terms of potential. As our quantum-based models for machine learning continue to improve, while companies like IBM, Google, and D-Wave are building more enhanced quantum hardware, this will enable us for more accelerated pattern recognition and classification, as well as new applications in different industries, for example, for drug discovery and also financial risk analysis. Thank you so much for taking the time to listen to my presentation on my work. If you want to learn more about the full implementation of the code, feel free to visit my GitHub page and check out some papers I wrote that will go on a more in-depth explanation on this. Thank you. I really appreciate it.